Good morning, everyone. Myself, Sheila S. I will be taking Verilog HDL for this semester. The course consists of how to program an hardware device. So, till now, we have learned many programming subjects like C programming, microcontroller, all these things you have learned. They are all application oriented program, but here what we are doing is we are designing the corresponding device, and to design the device we are using some CAD tools. So basically, first we need to understand why the requirement of this design or this programming language is required. The first thing is, whenever we are going to consider any hardware circuit, so we if we rig up any circuit and then we have to check the functionality. So we have to find whether the circuit is working according to the requirement or not. Suppose if it is not according to the requirement, or if there is any error in the circuit, debugging will be difficult. If for example, if I'm going to consider a simple half adder circuit, so there the circuit is very simple, so we need to check whether the gates are working properly and if the connection is correct, and then we will be checking for a given input whether we are getting given a required output or not. This is basic thing. Suppose if we imagine the complexity of the circuit increases, so from full adder to, let us consider 4-bit parallel adder. So in that case, 4 full adders will be concatenated to get 4-bit parallel adder. So there also, after making the circuit, we will be giving the input and we will be checking whether we are getting the required output or not. If there is any error, once again we have to redesign the circuit, isn't it? So this process happens repeatedly. And whenever we are going to consider any circuit, so usually these circuits are made up of transistors, especially the digital circuits. When we are going to consider, it will be having two basic levels, that is logic 1 and logic 0. So as a result, we will be using the switches, transistor switches. So using the transistors, we have to first consider the logic gates, and from that logic gates we have to make the corresponding circuit. For example, if I am going to consider an AND gate only, I need at least two transistors, isn't it? So using the two transistors, first I have to design the AND gate, and then I have to check the functionality. If it is working, then we can consider the same circuit multiple times to get multiple AND gates. Similarly, as the circuit complexity increases, imagine for example, if you are going to consider an ALU circuit. So when I am going to consider ALU, so mainly it will going to perform arithmetic and logical operations, isn't it? The basic arithmetic operations, what we are going to do is addition, subtraction, multiplication, division. Like this, we are going to do the basic arithmetic operations. So to do that operation, again we have to generate the circuit. So first we will going to design which particular components are required and how they has to be interconnected, and where the data has to be given, and where we need to check the output, isn't it? So as a result, what happens, there will be increase in complexity of the circuit, and also if the functionality is not proper, once again redesigning of the circuit takes place. So manually, until we get the correct result, we need to redesign the circuit and we have to check the output every time. So this will going to consume more time. And even this is for a simple circuit. If we consider a circuit of microprocessor or any motherboard, if you are going to consider, in all such cases the circuit's complexity is more. So when the complexity of the circuit is more, in that case we have to mm, invest more time on that. So to manufacture new devices and all, it will going to consume more time from the designers. So from the designer point of view, and to reduce the complexity, because error debugging will be very difficult if the circuit complexity increases. So in order to reduce that, the introduction to cat tool came, that is cat tool, computer aided design. So using that computer aided design, the designers were able to uh, find out the corresponding circuit connections. So first the designer used to think which particular device I have to create, and how to give the input, what should be the behavior, and later what are the components has to be used. When those components are used, how the interconnections has to be done, how the corresponding placement of the objects or the devices has to be done, everything the designer has to design, and next the corresponding circuit connection has to be done, isn't it? So for all these things we will be having a computer aided design. So there the designer will going to specify the requirement, according to that the system will going to make design of the device. Okay, but when the system is making the device, then the user has to interact with the corresponding cat tool, isn't it? So in the back end the device will be generating the circuit, but in the front end to communicate with the cat tool we are having HDL, that is hardware description language, where using this language we are going to describe how our hardware has to be our hardware has to be programmed, or our hardware has to be designed. Okay, so based on that, we are the corresponding definitions or the specification given in the program, the cat tool will going to make the circuit in backend. Okay, so using that, the designer will going to verify whether it is meeting the requirement or not. If it is meeting the requirement, then the circuit can be manufactured, otherwise once again the redesign has to be done. So that is why in the first module and in the first unit we are considering overview of digital design with Verilog HDL. There we will going to understand how the evaluation of the cat tool occurred, and the next how HDL, that is hardware description language, is useful in handling the cat tool, and what is the requirement. All these things we are going to study in first unit. And in the second unit, what we are going to study is hierarchical design concepts. So when we are going to consider hierarchical design concepts, so there are basically two ways we are going to consider. Means first we will be think of what type of device is required, and according to that required device we will going to think how the device can be designed, and in that design how actually sub part of the main design can be implemented. Means we will going to first understand the requirement, and based on the requirement we will be thinking of implementing the circuit. That is one type of design concept. And the another thing is we are having some devices. Using those devices we will be trying to find new, by doing interconnection of those devices we will be trying to find new circuits or new functionality. That is another type of design concept. So like this we will be considering the design concepts in the second unit. And also there one more thing what we are going to consider is simulation. Whenever we want to perform simulation, so usually for the design whatever we have done, to check the functionality of the design we are going to considering simulation. That is why when we want to perform simulation, first the design has to be ready, and when once the design has to be ready, the next thing is how to give input and where to observe the output. So that we are going to do in simulation. So in that simulation, how a simulation can be applied for the design, all these things we are going to study. Okay, so in the second unit we will be studying the different types of design methodologies, and as well as how the design can be tested, functionality of the design can be tested. And next what we are having is second module. In the second module, the concepts, that is the basic concept. See, for example, if you are learning any particular language, means you should know the basics of that language. For example, if you are learning English only, so when we are learning English, first we should know what are the alphabets are there, and what are the vowels, what are the consonants, how a word can be framed, and how we can use the words. All these things we should know, how the grammar has to be used, all these things. That is the basic requirements to learn the language. In the same way, if you consider C programming, there also you should know how to write a program, what is the corresponding syntax, all these things, how the programming concepts will be done. All these things can be understand, what type of data we have to give, what type of output we have to expect. All these things we should know, and how it will be executed, all these things. So for that, we are having basic concepts. In the HDL also, what are the conventions, means what type of keywords, or else what type of data we are going to use. All these things we will be studying in basic components, which is which are the basic requirements needed to write HDL programming. And next thing what we are having is modules and ports. So here, if I consider any particular device, so to interact with the device, we need some IO port. For example, if you take your mobile phone only, so in that, if you want to use your mobile phone, you should know how to switch on the device, and after turning on the device, how to use the device. So you know that in nowadays smartphones we are using, so to use the device we will be considering the touch screen. So when the touch screen has been considered, then where the input has to be given, how to unlock the screen, how to read the message, all these things we will going to do. Means we are interacting with the device through the touch screen. We are only giving the input, and then we will be observing the output that is displayed on the screen, isn't it? So that is why in the modules and ports we will be considering how the connection, the ports connection will be done with the device. So that if I consider any device, we should give name for the device, and the corresponding IO ports, what type of ports we have to declare for which design. All these things we'll study in modules and ports. And in the third module, what we are going to study is two types of programming. That is, one is gate level modeling, and the another one is data flow modeling. So if I'm going to consider gate level modeling, so there what happens is the designer should know which complete details about the circuit. So that is why the designer should know which particular gates I have to use, and how they has to be interconnected, all these things. So for example, in the previous instance only I told, if I consider half adder, basically I need at least two gates, AND gate as well as XOR gate. So when I'm going to consider AND gate, again how that AND gate has to be implemented, so that will come under transistors. So how many transistors, and how the interconnection between the transistors has to be done to perform that function of AND gate operation. Similarly, if I'm going to consider XOR gate, again how that XOR gate has to be implemented. So the designer, if he know that I need to implement half adder, and if he know the logic circuit, that which particular gates I have to use to get the corresponding function of half adder, then I'll be using the corresponding gates only to write the program. So that comes under gate level modeling. Means if a designer is having complete knowledge about the logic circuit, then he will going to write gate level modeling. He will be knowing how the inputs has to be given, which gates input should be connected to which gate output. All these things he will be knowing entire circuit. Then only he can go for gate level modeling. And also whenever we are considering gates, so obviously every hardware device will be having its own delay. So when we are going to program for a gate, then we should consider what is the corresponding minimum delay when I give an input, how much time it will take to execute and to give the output. So that comes under delays. So by giving the delay input also, how our device is working, whether it is working according to our requirement or not, that will be considered under gate level modeling. And the next one what we are having is data flow modeling. In this data flow modeling, what happens is the designer will be knowing what circuit he has to do, but what operation the circuit has to do. But the designer is not aware that how the circuit connections, which particular gates has to be used, and how actually the circuit has to be connected. So this knowledge will not be there for the designer. So when the designer is not having any knowledge regarding the circuit, but he know how his data has to be processed. Suppose if he is having the corresponding A and B inputs. So I'll take an example of half adder only. So to get the sum output, the designer don't know which gates he want to use, but he know to get some output he has to perform XOR operation of two inputs. So he know how the data has to be processed, but he don't know anything about the circuit. So in such case, we will go for data flow modeling. So there we will going to specify how actually my data has to be processed to get the output. And once again, its functionality has to be checked. After writing the every program, we need to check the functionality. So when I give this particular input, if I'm getting the corresponding output, then the circuit is working. Okay, so like this we have to check the functionality. So in data flow modeling also, I'll know the expression, like by using uh, which expression I can, or by using which particular operation I'm going to get the corresponding output. In that case, for if I give any inputs, whether it is working properly and I'm getting the output, it has to be checked. Okay, for that also we are going to use simulation, which we discussed in the first module. And the next what we are having is the fourth module. In that fourth module, we are having behavioral as well as behavioral modeling and tasks and function. So first let us consider behavioral modeling. So in this behavioral modeling, the name itself indicates the behavior of the device. Okay, so here the designer will not be having any idea regarding the circuit as well as how the data has been processed, because designer doesn't know which gates are used, how many gates are used, how they are interconnected. He is not bothered. And similarly, designer is also not bothered how my data has to be processed. So he is having only knowledge that he should give a input and he should get a corresponding output. That's all. Only regarding input and output he know, not about the circuit and its operation. Okay. So in such case, we will be going to consider behavioral modeling. Means we are explaining how my device has to behave. That is why it is called as behavioral modeling. So there we will be coming across many statements like conditional statements or control statements. Because see, since the designer doesn't know anything about the circuit or its operation, he will be knowing if this is the input, what should be the output. Otherwise, if the corresponding condition is not true, then he has to check is there any other type of conditions. If such conditions exist, what should be the output. So like this, he has to mention different conditions. For these conditions, what type of output he has to get. So that is why we will be considering conditional statements. And when a particular part of the circuit, I mean, when the corresponding design has to work, and at what time it has to read the input and when I should get the output, all these things. So they'll come under behavioral modeling. He just describes the behavior of the circuit. He will not going to do any other operation, but he will describe how his device has to work. This is regarding behavioral modeling. And next, what we are having is tasks and functions. So, in C programming as well as in microcontroller programming, you have learned regarding functions, even procedures also. So, whenever we are going to consider any task or function, so usually when a part of the program, or if some operation has to be done repeatedly, then instead of writing the program that many number of times, we are going to use functions. So where the length of the program will be reduced, but the same function can be called n number of times. And similarly, we are having tasks. So tasks and functions are different. And so where the function will return a value, but when I'm going to consider task, it will just perform the task and it will come out from that path to the main program. So like this, we'll study in detail regarding tasks and functions. Okay. So using these tasks and functions, we can effectively write the program, because whenever we are using functions and tasks, so we should be knowing that which part of the code has to be used repeatedly and which operations has to be done at what particular instance. All these things we will be knowing. So as a result, the main big design will be divided into small parts or small functions, and we'll be writing those functions and we are using them effectively in the main program. So that is why in the first three modules, basically we will going to write how to write the program. Sorry, we will going to understand how to write the program, and some more maturity will be achieved while writing programs using tasks and functions. So that we are going to consider in task as well as function, and also we're going to understand what is the difference between task and a function. So usually whenever we are going to consider functions, we'll be giving input and it will be returning a value. But when we are going to consider task, so there we will be having input as well as output variables also. So there, uh, for a task, it is not compulsory that it should return a value. It has to perform the task and come back to the main program. But for a function, it has to return a value. So like this, we will be considering the corresponding difference between tasks as well as functions. And next, what we are having in the fifth module is useful modeling technique. Okay, so till now we have considered regarding how basically the programming can be written, and when as the design matures, how we can use task and function. And in this useful modeling technique, what we are going to do is still using these tasks and function, how actually the compilation has been done. You see, for example, some part of the code has to be done in some platform, and the another part of the code has to be done in another platform, or else some part of the modules or some devices should be activated for only particular amount of time, and after that it has to be deactivated. And whenever any particular interrupt or whenever any particular condition occurs, then only some devices has to be activated. In all such cases, we are going to use useful modeling technique. So when we are going to study the complex circuits, so there this usefulness of the modeling technique will be experienced, because as the complexity increases, for example, if I'm going to consider the motherboard only, or else if you are going to consider your mobile phone only. So in that mobile phone, it is having n number of devices inside that, isn't it? Every time all the components in the circuit will not be utilized. Only at few at particular time, particular circuit will be activated. For example, if you want to play any particular audio, or if you want to play any particular video, so there what happens, it will going to select that particular path, and then the corresponding audio playing has to be done or video playing has to be done. By that time, call receiving circuit or message sending circuits, these circuits will be not working. If you are using that particular operation, means if you want to make a call, then only that part of the circuit will be used. If you want to send any message, then that part of the circuit will be used, otherwise it will be idle, isn't it? So there, you should know when a particular flag or when a particular requirement arises, then the corresponding circuit has to be used, otherwise it should remain idle. So all such things we have to mention in our circuit device, sorry, in our circuit design, because we are designing the entire device. So we need to take care at what time or at what condition which part of the design has to work and which part of the design should not work. So these modeling techniques will going to help when the complexity of the circuit increases. For simple circuits, what you are going to do in lab, there you may not find this type of experience. But when we are going to think in a higher way circuits, so for example, if I'm going to consider working of a microprocessor, or else you just consider microcontroller only. You have seen washing machine, refrigerator at your homes, everything, isn't it? So there, when the washing machine has to work, when you press a particular button, which mode has to be activated, there you will be selecting a particular mode, and then you will going to turn on the machine. Then in that case, only that mode has to work, and all other modes should not work. Okay, so these things according to the requirement, required part of the design has to be enabled. So that we are going to study in useful modeling technique. And the next one what we are having is logic synthesis with Verilog. See, till now we discussed only regarding how to write a program, isn't it? But we have not discussed regarding how the circuit will be generated. So in the fifth module, we will going to learn that. That is, in logic synthesis with Verilog means the synthesis will going to develop the circuit for whatever the program you have written. Okay, so if I write program using data flow modeling, how the circuit has to be generated, if I use any particular statement, according to that statement, how the cattle will generate the circuit. If I write any conditional statement like if statement, for loop, while loop, all these things. So when I'm going to use these things, how actually the circuit will be designed by the CAT tool, that we are going to study in logic synthesis. Means whatever the program user will going to write, it is a high level program because only user can understand. So using that, your CAT tool has to interpret, and then it has to make design of the circuit. So first it will going to do logical design, and then if the design is working properly, from that logical design, the corresponding switch level or gate level design can be done. Yeah, one more, we have considered three types of programs like gate level, data flow, as well as behavioral. One more method of modeling we are having, that is nothing but switch level modeling. So switch level modeling means the designer will have complete idea regarding how the transistors are interconnected, how many transistors has to be used, and how they should be interconnected, all these things, entire basic circuit will be known to the designer. Then he can write switch level programming. Okay, but that is not there in your syllabus. In your syllabus we are going to study only these things, means how the cat tool has been I mean, what was the requirement for the evaluation of cat tool, and what was the need for the emergence of HDL. All these things we're going to study. And again, in HDL, what type of languages? There are mainly two types we are going to use. One is Verilog HDL, and the another one is VHDL. VHDL is nothing but very high speed integrated circuit hardware description language. Verilog HDL is nothing but verifying logic, verifying the logic of circuit. So that is why it is called as Verilog. Verify plus logic will give you Verilog, and HDL is nothing but hardware description language. So using these languages, how to write the program. In your syllabus, you are mainly having only Verilog language, not the VHDL. So here, the main difference between Verilog and VHDL is, compared to VHDL, Verilog is bit user friendly. Okay, we can easily see, for example, if we miss to mention some part of the information, then it will going to presume. See, for example, if I am going to consider two 8-bit numbers, so instead of considering 8-bit number, if I give only 4-bit number, that is one nibble, in that case it will do the extension for 8-bit, and it won't show any error, it will read the data. But if I'm going to consider Verilog VHDL, there if I specify it as 8-bit, I need to give 8-bit input. If I specify it as 4-bit operation, I have to perform only 4-bit operation. So like this, it is very specific. We have to clearly mention how it has to be done. But in case of Verilog, it is somewhat easier for the programmer. So in this course, we mainly will be learning Verilog coding. And the next, what we are considering is the corresponding objectives of the course. So what are the main objectives? So objectives tells that what you can achieve. So from this course, what you can achieve is, you can able to learn different Verilog constructs, means how to write program using Verilog HDL. And next, familiarize the different levels of abstractions in Verilog. So I told we are considering gate level modeling, data flow, as well as behavioral. So depending on the requirement, we will be using different types of modeling. The writing program is nothing but abstraction. So different level means, if it is gate level, means if I know complete circuit in the, that is logic circuit, then I can go for gate level. So that is known as one level of abstraction. Similarly, if I know how the data has to be processed, I'll go for data flow modeling. If I know only behavior of the circuit, I'll go for behavioral modeling. So like this, we will going to consider different levels of abstraction. Okay, and the next one what we are having is how to use tasks, functions, and directives. So mainly directives will going to tell what the corresponding software has to do if this particular directive is mentioned. For example, if you want to display, so it has to tell the system to display a particular given value on the monitor. Okay, so to give this information, we are going to use the directives. Okay, so like this, we are going to use Verilog tasks, functions, as well as directives. And the next what we are having is understanding timing and delay simulation. So here, when since we are considering the practical device, so every device will be having its own delay. So we have to analyze the delay taken by the circuit, because as soon as I give input, I mean, I won't get the output. At least some nanoseconds of delay it will take, because it has to process the data, isn't it? And then it has to give the output. So that is why whenever we are going to consider timing and delay as well as simulation, means in a simulator without delay I may get the output, but when I manufacture the same hardware circuit, I will not going to get the output without any delay. So by giving the delay input, I need to check whether in a specified delay I am getting the proper output or not. So if I download it for the sorry, if I download the same design for manufacturing, then when the hardware device has been implemented, then once again I need to check with, when I give the input, whether it is taking the delay specified within the simulation data, because those delay has to match. Suppose if this device is taking more delay, means the other devices, depending on the first device, the other device operations will be affected. So that is why we have to observe properly whether we are getting the corresponding delay, or whether our device is working with more delay or less delay. All these things we have to analyze, so that we are going to consider as understanding of time and delay simulation. And the next one, what we can consider is how the circuit will be built. What is the impact? Because impact in verification means, see, when I design any particular circuit, if I am not going to check whether it is working properly or not, then I cannot guarantee that my circuit is 100% correct. So that is why I need to verify. So after every design, if I am keep on verifying and checking the functionality, then the errors in the design will be reduced, so that we can generate an error free circuit. And without considering the hardware, first only we can check the functionality of our design, and then when everything is okay, then the circuit can be implemented, so that it will going to reduce the manufacturing cost. Because see, if we do not have cat tool, imagine what happens every time we need to rig up the circuit, and every time we have to while checking the functionality, if there is any small error, debugging the error will be difficult, it will take more time. And suppose if there is any damage, or if there is any failure of some part of the device or circuit, in that case, identifying that and once again replacing the corresponding component and once again redesign the circuit and checking the output, it will consume more time, isn't it? So the impact of verification is more using the cat tool. And similarly, for every given design specification, how the circuit has been developed in the cat tool, that we are going to consider in synthesis. So the main objective of the course is to study Verilog HDL language, use it effectively, and while writing the program, you have to keep in mind that we are designing the actual hardware device. So every device will be having its own delay. So how to simulate with the delay, and to check whether we are getting proper output after this delay, and how the circuit will be built. So these things the students has to understand. So that is the objective of this course. And the next one what we are having is, what is the outcome? Means the syllabus is designed by keeping these objectives, that student needs to understand coding properly, and he should able to verify the circuit and its design, and he should know how the circuit will be generated by the cat tool. This was the objective. And when once you undergone this course, then what is the outcome? What actually you are going to learn? That is known as course outcome. So here mainly we will be getting these course outcomes, that is you will be able to write programs in different levels of abstraction. And next, you will be able to check the functionality using the simulator. And next, whenever any design is specified, you will be able to decide which type of abstraction is required for a given design. And next, since you have studied modules and tasks, sorry, functions and tasks, you can able to effectively use these tasks and functions. And also you can give delay and you can able to verify the circuit operation. And also, since you know how you will be studying how the circuit will be generated by the synthesis tool, you can able to interpret the corresponding constructs, how for a given particular set of instructions, how the circuit will be generated. All these things you can able to do, you will be doing this. So that is what the course outcome we are going to consider. Okay, so this is regarding your syllabus.